everyone. Nice to be here at this Triad conference. My name is Haldo Sponton. I'm a VP of Technology, and I'm the head of Artificial Intelligence Development at Globant. And my idea today is to present yourself this augmented coding tool that we have developed. And as you may see in the motto, it's the idea of using artificial intelligence techniques to basically augment software development capabilities, to basically help developers code faster, code with less errors, and code more efficiently. I am based in Montevideo, Uruguay, something that I forgot to mention, so greetings from South America. First of all, I want to mention something. I think everyone here is living a tough situation. The world is living a tough situation today. I know US is not having the best time today, and here at South America, we are also not apart from that. We are living a harsh time today. So I hope everyone is enjoying this content, is enjoying this conference from home, and I hope everyone is safe and with their family. It's nice to be virtually connected in this tough situation. So again, back to augmented coding. What is this? Basically, it's an ecosystem of models, an ecosystem of AI tools to basically, as I mentioned, elevate engineers' coding experience, basically help them code faster, help them code with less errors, help them code more efficiently, basically by solving their questions, by solving their problems, by answering their problems. We started developing this tool like 1 year and something ago, but nowadays this tool has become more relevant because when we were in the office, if we have any doubt, if we had any, problem with our code, we probably could just turn our chairs and find a colleague, an expert in a certain technology, to basically have a 5-minute stand talk and ask whatever the doubt we could have, or even just meet at the computer and see together the code and try to solve the problem together. But we went from this to this. Nowadays, we are working alone at home, and it's not a matter, maybe we can meet this expert, but it will probably involve to, set up a call, trying to find a common time slot in the agenda to meet, and it's not as direct and as immediate as before. So these kind of tools that basically answer questions to developers and can basically act as a little expert working besides me to basically answer any question I have, today is way more relevant than before. So my agenda is pretty basic. I want to cover 2 big points here. The first of all, I want to talk about natural language processing, and I want to talk about this NLP revolution that we are living today. And I will explain why I am talking about a revolution in the natural language processing or natural language understanding. And second, I will explain what is this augmented coding and why this is related to the understanding of natural language. So first of all, what is natural language processing? Well, I assume you are familiar with the term, at least you have heard this term a lot. But basically, natural language processing is a technique to enable computers to make sense of the human language. And it's not a novel concept. It's not new. It has at least, 70 years old. But in the last decade, we have witnessed an unprecedented leap in NLP techniques and technology advancement. And much of that progress is enabled by what we call deep learning or deep neural networks. So why am I talking about a revolution? Well, there have been several revolutions inside the field of artificial intelligence. The field of AI, it's pretty broad, it's pretty big, and there are many subfields inside that are pretty big and interesting. For example, in 2012, the first neural network-based algorithm, in particular convolutional neural network-based algorithm, basically outperformed every other approach to image classification. That algorithm was called ImageNet, and that was the start of the revolution in computer vision inside AI. In 2015, we witnessed a revolution in voice recognition. In fact, that was the year when a deep learning algorithm outperformed or improved a metric called word error rate. And the word error rate, for that algorithm was less than the word error rate for humans. And that in that time, voice understanding for computers started to spread, and now we have many voice assistants around us. Today, we have this revolution of NLP. I will go with a timeline in a couple of slides of NLP, but basically, in the last 2 years, we have seen the evolution of this technology called transformers, and it's not these robots in the movies. Transformers is a deep learning architecture that is particularly useful and particularly successful when dealing with language understanding. So again, as I said, NLP is a technology to help computers understand our language, and this is not an easy task. As I mentioned, we have been dealing with this for the last, 70 years. This started like in 1954 with this Georgetown IBM experiment. It was basically the first attempt for automatic translation in that time. It was developed by Georgetown University together with IBM, and the experiment involved the completely automatic translation of around 60 Russian sentences into English. Maybe almost 20 years after that, we had the first statistical approach to text analysis, and that is called TF-IDF, or Term Frequency Inverse Document Frequency. This was pretty useful, and in fact, it's an approach that is already useful today, and it's basically statistics that you can make in a corpus and in documents to basically reflect how important a word is to a document or a collection. And then 30 years after that, we had the first application of neural network models to text analysis, to natural language processing. Not too much until 2013, when we first have this model called word2vec, or in other words, basically the first approach to convert words into numbers. We can capture the semantic content of each and every word. And let me just stop 1 minute on that, because this concept is pretty important. Word2vec gave us the possibility of representing the words as numbers, but not in any way, representing the words as numbers in the way that the operations with those numbers have some meaning for our language, have semantic meaning. As you may see, the relationship, for example, between the word king and the word queen is the same relationship between the word man and the word woman. The same happens with verb tense, or the same happens with, for example, countries and capitals and stuff like that. And this is basically the result of training these algorithms with huge amounts of text. So basically, given a huge amounts of context, I can, or the machine can, understand the semantic relationship between words. This is a pretty big concept, because this opened the door to everything else that happened from that time. Continuing the timeline, 2014 and 2015, pretty big years for developing of this word vector representations with glob and fast text, more evolved versions of word2vec. And then in 2017, as I mentioned, these models called transformers. Transformers is basically an evolution of other recurrent models to understand sentences or documents with a lot of memory. This gave models the ability to understand text, even if the context was not close in terms of proximity in the text. This was a huge advancement, and nowadays the state-of-the-art algorithms in terms of NLP are based in transformers technology. 2018, we had materializations of the transformers idea into Elmo, GPT, and BERT. I assume that you have heard GPT at least, or BERT somewhere in the literature. Last year, we have an extended version of transformers, the second version of GPT, a robust version of BERT called Roberta, and this year we have the evolution of GPT called GPT-3. And these models are powerful. This is an example of text generation. Models today are not just able to analyze text. They can generate text, and they can generate meaningful text, coherent text. In this case, for example, this model is asked to complete the sentence, to basically continue the text addition work that some humans start. For example, a human just typed, "Recycling is good for the world," and then typed, "No, you could not be more wrong." And then just let the machine do the rest. Let the machine continue that idea. And if you see the model completion or the machine written text, basically the machine starting saying, "Recycling is not good for the world. It is bad for the environment. It is bad for our health, and it is bad for our economy. I'm not kidding. Recycling is not good for the environment," and starts, explaining, detailing a bit more the explanation. This is from the technology perspective, from the text understanding perspective, this is pretty powerful. The machine is actually generating coherent text, meaningful text, and is actually capturing the idea that the human expressed and exploiting that idea with new text. I will go back to text generation in a future. Last thing about NLP, today we are living this revolution, and the result of this revolution is that today at least 10 models outperform humans in what is called Squad or Squad 2.0. And Squad is basically a data set, a curated data set of questions and answers. That is basically, the task is I ask the machine to answer a particular question with a given context, or dismiss the question in case of the answer is not living in that context. And as you may see in the ranking, given the F1 score, for example, the 10 first models are outperforming human in that task. So it's pretty amazing, and that's why we are living this natural language processing revolution. But what does this have to do with code? Well, all these ideas can be applied to code. Code is not more than just another language, just another way to express the way we need things, to express instructions, to express something we want the computer to do in a particular scenario. So we started to do that. We started to basically apply the same ideas, and I will go back to the semantic representation of text, the basic idea behind NLP, to code, to pieces of code, to trying to understand or to capture into a semantic representation the functionality of a piece of code. As I mentioned, we combine these natural language processing techniques with some custom deep learning, some custom neural networks, basically created for this source code understanding or this programming code understanding. And what we can do is, again, capturing the semantics behind pieces of code. And that's the most important result behind augmented coding. Of course, as I mentioned, these text algorithms are trained with huge amounts of text. Well, we have a lot of code to train the algorithms. We have now around 750 million lines of code in the 4 languages that we support today. And we have been pretty careful trying to curate this basis. It's not that easy, it's a lot of code, but we have trained this model to understand Java, to understand Python, to understand C#, and to understand JavaScript. And in fact, in our roadmap, we have other languages, for example, C++, for example, TypeScript to complement, the front-end world, for example, Kotlin, or even Golang. What are the main functionalities? What can I expect from applying these same NLP techniques or ideas into code? Well, first of all, I will start with the second one, because it's like the basic understanding of code that I was mentioning. Since the model can capture the code functionality and represent that functionality or semantics into numbers, I can basically compare 2 pieces of code to see if they are actually implementing the same functionality, even if they are not using the same words, the same instructions, the same structure. I can compare 2 pieces of code. And that gives me the ability, or give the models the ability of detecting duplicated code. Because if 2 pieces of code are implementing a sufficiently similar task or functionality, I can say, or at least I can raise a flag to say, these 2 pieces of code could be duplicated. This could be implemented in a more efficient, more maintainable way. When we add to this code understanding model, when we add a natural language model, for example, an English model, I will get this semantic code search functionality that I was mentioning at the beginning. I can combine the semantic representation of text with the semantic representation of code, so I can basically capture what a developer wants to say when they ask or when they type a question, and relate that with the implementations that I have in my code base. And then I can answer the question with the most relevant piece of code in each and every query. And that's one of the biggest functionalities that we have here. It's like an intelligent way to navigate the code just by asking for a functionality or for something I need to implement. Then something we can do, and I'm going to show some examples today. This was kind of a side effect of all the research we did, and maybe I'm going to misuse the language here, but we can use the models like in reverse, like backwards. It's not just like that. We have to define some decoders and stuff, but just for the matter of the understanding, we can give the models a piece of code, and the model will try to write or generate a sentence to explain what that code is doing. And that sentence has to make sense in English, and it has to explain the functionality of the code that was given as an input to the model. And that's automatic code documentation. I can automatically, or the model can automatically document a piece of code. And all these functionalities are basically given to the developers in 2 different interfaces, both in a centralized web client where I can see all the projects inside my organization, and I can navigate all the projects that I want using this semantic code search and stuff, or I can have it installed in my IDE and basically ask questions directly from the IDE to my local code or to remote code or remote projects. And that's the basic functionality of what we have today. Of course, we have in the future some other ideas on how we can apply this, for example, into code completion, or for example, into code generation, maybe in the future. That's something that, at least in the academic world, is something very, I don't know, it's prominent, it's growing, it's not solved. Of course, this is an open problem in the academic world, but it's very exciting to be researching in this field. Just a double click into two of the particular functionalities that I mentioned. The semantic code search, just to show you examples, and maybe I can show some other examples with the IDE. Again, the idea of semantic search is to search for code by meaning. It's the opposite or different from the lexical search, or searching the code by keywords or regular expressions or stuff like that. I don't need to know how the functions are called. I don't need to know how the classes are called. I don't need to know any particular keyword in the code bases where which I am working with. In this example that we see on the screen, this is just like a toy example, but it's just to show the power of NLP here. We have this repository that is called Teammates. It doesn't matter, it's just an example repository. But this repository is managing students, instructors, institutions, and entities like that. If I type in GitHub the question seek pupil, this is not offering any answer, not in the code, not in the issues, not in the documentation, nothing. But if I do the same query with augmented coding, with our semantic code search engine, the most relevant result that I find is this search for student function that is basically searching for a student given its name. And this is the power behind this. This is basically understanding the semantics behind seek pupil, and not even it doesn't care about the words by themselves. It cares about the meaning of the words that I'm using. And that's why this function, search for students, pops up the most relevant function for my query. In the automatic code documentation world, this is just, I'm going to show some examples, but this is the kind of documentation that these models could generate. And again, the process here is basically the model is taking this piece of code as an input and generating the text, just picking word by word from a vocabulary, the same way we could make up a sentence in our mind. This is pretty, at least from my perspective and from my AI background perspective, this is pretty awesome. And I know we have to work up a lot more on this because text generation is a tough problem, but this result is very promising. It's very good. For example, in this case, the machine generates a text that is called consumes the next character from the source and returns it as a string. And it's pretty much what the function is doing. Another example that the generated documentation was notify the device that the given device has connected. And this examples helps me to show a bit of the problems that we could have in text generation, because it's, as I mentioned, it's not an easy task for computers to generate text. And in this case, you may see that the phrase it makes no sense. It is good, but it's not perfect. You can see that it's not written by a human. So this is the kind of things that we need to work on. You know, when we deal with data generation, not just text, when you deal with generation, you need some other metrics on top of the generation just to make sure that what you are doing makes sense. And in this case, what we are working on today, it's on very particular metrics to reinforce the output of this generation algorithm. But we are very excited with these results. So let's jump to a quick demo of the platform. I will do it in the web client or in the IDE, it doesn't matter, but I just want to show a bit more about the power of this combination of natural language understanding and code understanding. So if I may, I will jump to my code here, and I will show just some examples in Java, for example, just to start. I will go fast, just 2 or 3 examples, just for you to have the idea. This is just a search bar where I can ask whatever I want, and I will start with a very short example, very easy example for the algorithm. That could be, for example, sort elements. I cannot type and talk at the same time. Elements in a list. for example. And this is pretty easy. Of course, I will have different sort algorithms as an output of this query. Of course, the good things about this is like, if I do the same query with another code base, for example, a particular code base in a particular scenario, context, or wherever, the answers for that question will be related to that context, will be using the code of that context. But just let's go one step further of this. Let's just ask, for example, check if sentence can be read backwards. I'm doing a definition here. I'm not asking for a particular word. I'm doing a definition with a functionality that I need. And the result for this, the most relevant result, is a function called isPalindrome. That is basically what I defined before. And if you see here, there is not even a word mentioning what I asked for. There's not a word saying check or sentence or read or backwards, nothing like that. And this is the power of using the combination of the semantic representation of text and the semantic representation of code. These models can actually represent both functionality and semantics of the query and tie them together. I can do, for example, one example in C#, going a bit farther, just for you if you are more a C# lover, and I will do another search. For example, I find numbers that can only be divided by themselves. Again, I'm trying to use, definitions instead of using particular words or keywords behind this. And of course, the result is get all the prime numbers. And again, this could be like I'm using basic code, I'm using basic examples, but the power behind this is the ability to use these algorithms in different contexts, because language models are pretty powerful and they can understand different contexts. And what we added here is the ability to relate that understanding to code understanding and to be able to tie the power of NLP with the power of functional extraction of or semantic understanding of code in different languages. So let's go back to the presentation. Some numbers for you. We have done some studies here. This has been like pretty technical, but we have done some studies here, and we know that most of the managers of innovative companies, they think that AI can or will benefit their work. We know that. We have done some tests, A/B testings, and we are using this augmented coding tool in our projects, of course, in what we develop in-house at Globant, and we have seen up to a 30% of increase in productivity when teams are using augmented coding. Of course, this number comes from different experiments, A/B testings, and stuff like that in different languages. But the thing is that developers actually go faster with this tool. And when we restrict that to junior talent, for example, we see that they get more benefit with this because they actually tend to look for code using these expressions. They have these doubts. So when we restrict the analysis to only junior people, we see up to 50% of increase in productivity in this population. So we actually believe that this tool could help in different code development scenarios. So that's it for today. I hope you find this approach very interesting. We are pretty excited both with the research and development process behind this and with the results and the product that we are getting out of it. If you have any doubt, you can contact me with this email address. It's haldo@globant.com. Or if you have any doubt or you want to know more about the tool, you just have to go to augmented.globant.com/coding. Again, I thank you all for being here. I thank you all for paying attention, for sharing this virtual space together. And I wish you continue being safe, being at home. I say hi and goodbye from Montevideo, Uruguay. Again, my name is Haldo Sponton, and I hope to see you or to be together soon. Thank you all.